Excellent, that'll do. So today I'm going to be... It's difficult. So when I submitted this talk, I gave it the title Machine Learning in InfoSec, and then realized that Machine Learning in InfoSec is actually like a 12-week university course. So what I'm going to do today is talk a little bit about some of the things me and some friends have done to apply machine learning in a security context, to do some half interesting things. One interesting project, one very boring one. As well as give a flavor as to what machine learning is and try and demystify it. Because if I can do it, you can do it. So about me. I'm a security consultant with NCC, along with probably about a third of this room, I guess. I was working on my PhD applying some AI techniques to security problems before I dropped out to be a pen tester. Prior to that, I was a software engineer, and I did some blue team work for the university I was working on. So I've kind of seen InfoSec from a bunch of different sides, despite the fact that I haven't actually been here for all that long. So what we're going to do is we're going to talk a little bit about what machine learning is, what it can do, what it can't do, how it works, and how you can do the thing, because it's super interesting and it's useful for the kind of projects and to tackle the kind of problems that traditional approaches don't really work. So it's not magic. It doesn't fix everything. And if you're going to use machine learning in a project, if you're going to try and use it to solve a problem, your solution kind of needs to be about it. You can't just sprinkle some machine learning onto your solution. You can't. Okay, well, we'll have like this. We'll have like 50,000 man-hours working on this one giant system, and then we'll bolt on a neural network at the end. It's very much the engine that drives solutions, and it generally breaks down into a bunch of different parts. You have data, lots of data. The more data that you have, the better. You have some kind of model, which is what's going to be interpreting the data that you've collected. You need to have some way of changing the model based on the data that you've got. And then once you have this trained model, that's when you can then apply it to new data that you gather as stuff comes on. The devil is in the details in terms of what your model looks like, how your model changes, and especially the data in terms of labeling stuff, but I'll get into that. So there are a bunch of different flavors of machine learning. It's a little bit like when people say, oh, I work in AI, which is what they used to say before machine learning became cool. AI gets treated as like this giant monolithic thing, when really it's about 24 different vaguely related approaches. In terms of the stuff that I'm going to be talking about, I will talk about neural networks because that's what's currently most fashionable. I'll also talk about genetic algorithms, which is it's a weird one, and I personally love the biology analogies that people have for machine learning because it's a little bit like saying, oh, I can be a vet working on canines because I sold hot dogs for a while. It's it's like that kind of illusion. It's rampant. You can also get like rule-based systems. So the neural networks and the genetic algorithms, they're very much a case of we're going to put together some stuff and we are going to throw some data at it, and it will change in some way, and we can't predict it, and it'll be fine. Maybe, probably. The rule-based systems and other things like that, they're a lot less, I guess the technical word is like stochastic. They're a lot less random. There's a lot less wishing. But you generally get those for things like expert systems for diagnosing conditions, or building navigation systems for autonomous robots, that kind of stuff. I unfortunately know absolutely nothing about that kind of thing, so I'll stick to what I do know. In terms of what version of machine learning is best for you, that depends entirely on your problem. I am a security person. I am not your security person. I highly recommend the book Machine Learning and Security. It kind of highlights why my talk can't cover everything I'd like it to, because I have 50 minutes and I can't just read. That book is highly recommended. It's primable, which is always helpful. So, genetic algorithms. I'm covering this first because it's less interesting than neural networks, and that way, I know that hopefully some of you had time to get coffee. You're currently riding the caffeine wave. Now is a good time to get through this. The basic idea is we have a problem that we'd like to solve, and we can generate random solutions to that problem. And we know how good the solution is, like we can measure it in some way, but we can't say, we can't take that knowledge of knowing what a good solution looks like and use it to build one. We can just be like, we need a car. I can't tell you exactly what kind of car we need, but I can tell you that this one is wrong, and so is that one. This one's okay. It's that kind of situation that this kind of technique is useful for. So what you do is you generate a whole bunch of random programs, whole bunch of random ones. You see how good they are, and you select maybe a proportion of those to go through to the next round, and then you fill up the population with a combination of like the babbies, if you combine two of the solutions together or more. You can take winners from the previous round and just change them slightly. And you can also fill in the gaps with like more randomly generated solutions to try and like add variety to the gene pool, so to speak. If there are actually any biologists in the room, I sincerely apologize on behalf of computer science. So you're generating random solutions, you're keeping track of the best ones. When do you stop? Normally when your AWS account runs out, or you have like a threshold of how good your solution is and you find one that matches it, or you just give up after a certain number of rounds and be like, okay, well, this is as good as we get. Roll out codebreakers. So I mentioned that I had done some PhD work. I was trying to apply genetic algorithms to solve crypto problems. The idea being that crypto systems are designed in such a way that even if you guess close to the right key, it's still wrong. And if you try and decrypt stuff with a slightly incorrect key, you're going to get very wrong output, which is terrible for things like genetic algorithms and other search-based techniques, because what you want is a gradient. You want to know when you're getting close to the right solution. So I was like, okay, fine. I won't try and do that. I will disturb my microphone, sorry. So what I decided to do was, rather than try and look for keys, I would try and look for attacks. So who here has looked at like linear cryptanalysis? Nobody. Cool. So how that works is you have your plain text, your message you're trying to encrypt. You have your ciphertext, which comes at the end of the last round. And what you try and do is, rather than guessing every individual round key, you guess the last round key, or a bit of the last round key. You push the ciphertext back through the cipher until you get like the input to the final round. And then there's a relationship between the plain text and the input to that round that you can exploit. Because that way you can guess part of your key, see whether your guess is correct. And if your guess is correct, then you move on to the next bit. So it's the difference between trying to guess every bit correctly all at once and guessing each bit correctly in sequence. That last bit is a lot simpler than the first bit. So what I wanted to do was to try and build a system that rather than try to guess a key, it tried to generate attacks. And I could tell how good an attack was. I couldn't like say, I want you to generate, I could say I want you to generate something like this. I want you to generate a linear approximation between the plain text and the ciphertext. Instead, what I did was I gave it the tools to build that. So the language that it used to build the programs was built of a bunch of different components. P for plain text, I for input to the final round, C for ciphertext, and K for a round key. I had some operations like XOR or AND or like general logical operations, and then I would get it to generate statements that involved those kind of operations and those kind of inputs, and just see what happened. Profit, kind of. So I don't know how easy that is to read from here, but what this is saying is that if you take the number 12,716 and you get the bit at position plaintext modulo 16, that is equal to the 0th bit of the input to the final round. I think. It's true enough of the time that you could use that to extract information from this cipher, which is cool. It's a useful thing. Not sure why it works, but it kind of did. This was another kind of answer I got. Yeah, I don't know what that simplifies to. And this is a problem with machine learning, because you ask the computer for an answer, and it gives you one, and it looks like this, and you've got no idea what this means. You've got no idea how you can use this as like a design factor for improving stuff. It just is a thing. Genetic algorithms are really cool for certain circumstances, but deriving explanatory power about problems is not one of them. Neural networks. This is kind of where you decide, okay, we don't care about explanatory power. We want a tool that's useful. Neural networks work a little bit like this. You have your inputs, and you have your hidden layer, and then you have your output. And you feed your data into, you split your data up and feed it to the input. They're called neurons. Again, sorry, biologists. They're called neurons. You feed your input data to those input neurons. They fire probabilistically based on the input. Those signals get sent to hidden layers. There might be more than one, depending on the kind of neural network you're making. And then those hidden layers, those hidden neurons, maybe fire. And then eventually you end up with output neurons, which, again, maybe fire. And that allows you to gather some kind of information about your input, which might be, this is a picture of a dog, or it might be, this packet is malicious. It's that kind of like classification problem that you tend to use things like neural networks for. So neural network neurons are not the same as brain neurons. They are either on or off. They fire, maybe, and there's a bunch of different ways of figuring out whether or not they should fire. So the strategies for figuring out when you should fire, there's a bunch of different ones. Some use like thresholds, like I am listening to 3 other neurons. If at least 2 of them fire at me, I will fire onwards. If the like combined signal from the neurons that I receive is above a certain level, then I'll roll a dice and try and match that probability, and then I'll fire. Or it might be I'll fire if inputs 1, 3, and 7 all fire. There's a bunch of different rules, and exactly what rules you use is more important for people doing academic research than people like us, because there's we can, especially when it comes to like explaining to clients, like I might have a job coming up to, in the next week or two to help build a learning tool for a very, very, very big company. I'm going to find it a lot easier to explain this kind of diagram than I'm going to find it to explain, oh, well, we have like 50,000 neurons with a threshold for firing based on whatever. In terms of the learning, so you have this, and you have neurons which might fire or might not based on what they see, but that's fixed, that's static. How does the actual learning happen? It's a technique called backpropagation, which is where you, during the training process, you feed your data into the network, the signal propagates, you see whether or not it gets classified as the right thing, or you see what the output signal is like. You figure out what the error is between what you were expecting and what you got, and you use that information to correct the probabilities of firing of all the rest of the neurons. Exactly how you adjust that depends. You ideally, if you want to get like a really accurate model that classifies things really well, you want to make small changes to the model based on your training data. You don't want any one training element to have like a disproportionate effect. Problem with that is it takes forever, and you need masses of data in order to like properly tune your model. You can cheat and make big changes, and it becomes very fast to train, but your model isn't necessarily going to be very accurate, which is great if what you're trying to learn is really distinctive, really straightforward. If you're trying to learn something that's a little bit more subtle, then that requires a little bit more thinking. I did mention that I was going to, in my submission, that I was going to talk about attacking this. It seems mysterious, but it's not. One of the very first things I learned in IT class in GCSE was the phrase garbage in, garbage out. If you can influence the training pipeline for a model, you can feed it garbage. You can say, oh, this picture of a tractor, it's actually a cat. I promise it's a cat. Or this packet, totally benign. The fact that it's like a PS exec for malware is entirely irrelevant. Definitely fine. And that way you can get the model to learn things that are false, which ruins its ability to be a useful tool for defenders. You can, if you have access to the model itself, but you can't influence the training, you can use that as essentially an oracle. You can make very small changes that don't affect the nature of your input or the thing that you're trying to escape notice, and wait for it to pass the model, and then send that instead. This is a little bit relevant for the next thing that I'm talking about. So there are applications like detecting malicious traffic, identifying malware, and also hunting Nazis, which is what me and a couple of friends have been doing in our spare time. So part of this is going to be showing you the kind of things we've found. Nothing is graphic. Nothing is racialized, but they're Nazis, and Nazis fucking suck. So apologies in advance for some very poorly constructed memes. So the A-team, which is what we band of people have been calling ourselves. I am the least interesting person on this team. We have Emily, who is former NSA, former CIA, US Army, works as a threat hunter for some private company based in the US. We have Ashanti, who they are a Rust developer and rapper, and they're really good at it, really good. How can you be good at so many different things? It's really not fair. And then you have me. Anyway, you can follow us on Twitter if you are interested. We've been working on a tool called Nemesis, which is a tool made to automatically find and classify white supremacist propaganda. It's aimed at Twitter at the moment, so we have a section called "Catch Me If You Can," written by our Rust developer, which looks at Twitter for certain keywords, finds images that come up in tweets, keeps them in a database along with the person who sent it, and the time and various other bits of metadata. We have the Nemesis model itself, which Emily trained. Bless her, she spent hours and hours and hours looking at like the most awful garbage you can find and like highlighting bits and being like, that's a swastika, that's a black sun, that's an odal rune. And that has got to be like one of the worst jobs I have ever heard of. Anyway, so she built the actual model, which is trained to represent Nazi propaganda. I did a bunch of plumbing, so we are now in a position where Catch Me If You Can runs, gathers images. The model written with TensorFlow, which is like Google's platform for machine learning. It's like a library. It'll classify the images. The information about bad images is then cross-referenced, and the people who are spreading really bad stuff get identified. Okay, so I'm going to show you examples of the stuff we found. Again, content warning, white supremacist propaganda. I am not a white supremacist. I don't condone being a fucking bigot. Here goes. So, here's a pretty easy thing that we found. It's pretty dark, both metaphorically and literally. It's a poster saying that Nazi youth are operating in this area with a fairly easy to identify swastika. Straightforward. We have this. Who's seen Roseanne, the TV show? Yeah. So Roseanne is Jewish, among other things. And she did this photo shoot as part of like a satirical magazine, if I remember correctly. And this is another important point about machine learning. Machine learning has no clue about cultural context or any other kind of context. You get it to train on a particular thing, and it will do that, and it will only do that. There's a story, I don't know whether it's real or not, about the US Army using neural networks to identify camouflaged Russian bases in like spy satellite photos. And they did it, and it worked really well in training, but then when they used actual data, it failed. And it turns out that all the photos of the Russian bases they trained it with were taken from one satellite, and all the photos of like benign areas were taken with another satellite. And what the model that they trained was really good at is spotting the flaws in the lenses in the satellite that generated the Russian base stuff. And so when they had other satellites, it didn't work anymore. You can never be quite sure what exactly about your training data the thing's picking up on, which is why like diversity is extremely important. Both the kind that this project is about and also the kind that is a bit more technical. So here's advanced one. That doesn't look like a swastika, except that it is. So the fact that the model was able to pick out that shape, independent of things like being black on a white background, or with like it's surrounded by redness, or it did actually identify the shape, and that's super exciting from like a machine learning point of view. From a let's ban all the Nazis point of view, I'm just glad that it's effective. Here's another advanced one. So that symbol at the back is the black sun symbol. An unfortunate side effect of doing this project is that I'm now au fait with white supremacist symbols, which I really wish I wasn't. That symbol is normally black on a white background. But the model was able to pick up the arrangement of shape with something in front of it. By the way, if you are on Twitter, avoid the hashtag RWDS, because it's full of people, unless you want to exercise your block button. Also exercise your report button. One of the things which we're wanting to do with this tool, potentially at some features, like automatically report people. I'm not sure Twitter has an API for that, but we're going to make one. Here's another example. So this is kind of what it normally looks like, except it's been slanted and covered with fire because, I don't know, their masculinity is under threat. And so we were able to pick that out still, which is quite cool. We have this clown, like, definitely an alpha male, with a very, very small KKK icon on their bathrobe. Anyway, it's small, but we noticed it, which is great. Yeah, so we accidentally classified this. Luckily, this is still in development, and so we haven't done anything like automatically with this stuff yet. But machine learning is not perfect. So what we're kind of hoping with this project is to do a bunch of things. Me, Emily, and Ashanti, between us, we're like every letter on LGBT. We're multicultural. We would be first against the wall if the Nazis were to take over. And like, we have no budget. We have no time. This is not sponsored by anyone. We're just doing this. You know, we're relatively successful in our own fields, but this is like hacked together in stolen hours. And we're able to automatically find stuff like this and this, and keep track of who posted it and who their friends are and what time they posted it and if they have location data put on. Yeah. So imagine what like Twitter could do. I am not saying that Twitter supports white supremacy or like tacitly allows it to happen. I'm just saying if they wanted to, they could fix it. And they haven't. Anyway, none of us are like machine learning experts. We just put together stuff with tools and like read tutorials and stuff like that. So if we can do that, you can do that. If you had 4 people working on the project rather than 3, you could probably do a better job than we did. In terms of Nemesis itself, what we need is like more training data, because it's just been Emily trying to put this stuff together in her spare time. And some of the classification is not perfect, hence like saying that Police Scotland is a... Anyway. It's currently supported by like Python scripts and cron. Like my software engineering like background, I used to work on like middleware for investment banks. What I really want is like a message-based system with lots of different independent parts, much more failure resistant. So that's the next plan. In terms of the actual data we're collecting, we're trying to do more to map out hate networks. We know some people who do more like political-based stuff that would be very interested in things like that. And maybe by demonstrating just how easy it is, we might actually convince media groups to do something about the goddamn Nazis. Anyway, here's hoping. So if you want to do the thing, we've been using TensorFlow, the Google framework. There's another library that sits on top of TensorFlow called Keras. Both TensorFlow itself and Keras are super straightforward to use. The tutorials, they're really good. There's a little bit of difficulty in terms of getting your input data to be consumable by the model, but they have example input data files, and it's fairly easy to like reverse engineer that. Yeah, so here's like an example bit of code, because this is a technical talk, I promise. So this is some Keras code, and that little snippet there, model equals sequential, that's defining a neural network. It's saying, okay, we have a densely connected set of nodes. It's expecting an input roughly of like a list in roughly this size. The neurons activate according to a ReLU model. I recommend reading that up. It's not actually important, but it helps you kind of understand what's going on. It's not important for this talk, so I'm not going to get into it. So you have like one input node, one input layer. We have like an activation set rule. We have another layer that's also densely connected, so every node is connected to every other node, and it activates with the softmax strategy. And that's it. That's a neural network in one line. Okay, it's a few lines for ease of readability, but It's super straightforward, and I highly recommend you don't need to be an expert in machine learning to pick up these tools and apply them to interesting problems, some of which are super pointless and boring, like my PhD work, and others have actual tangible results in the real world, like this thing we hacked together in our spare time. Highly recommend the TensorFlow tutorials. Again, I'm paid by NCC, not Google, so this is entirely because I like it, and I think that you should too. Caveat again about figuring out the input data, but it is reverse engineerable. It's not too bad. As like a general gist of this whole talk, machine learning is huge, and so I'm kind of sorry I didn't talk more about it, but I understand that we're overrunning a little bit. It's really useful when you know the kinds of things you want, but you don't know how to get it. So you can tell a computer, this is good. Good computer. Not so great when you don't know what you want. And it's if you can come up with a solution that if you can come up with like a classically programmed solution rather than use machine learning, that is probably a better choice, because then you have a little bit more explanation, it gives you a little bit more understanding about the problem you're actually trying to solve. Also, you can do the thing. I believe in you, all of you. I can do it, which means any of you can. Any questions? So the question was about adversarial images in terms of Nemesis. Like, have we seen people giving us malicious input? So far, no. But that's because our training is done offline. It's the input images they're not selected automatically, because you have to the way it works is you take an image like this, say, you draw a little box around the KKK icon and say, this is a KKK icon. And then the model gradually figures out what that looks like. By not giving attackers exposure to our input, like our training data flow, we're hopefully trying to mitigate a bunch of these attacks. Also, I don't know if you've met any Nazis. They're not actually very smart. I know that Weave, who's heard of Weave? Yeah, a few people. Don't Google him. He likes it when you do that. He was an administrator for a neo-Nazi website, maybe still is, left the US to go and live in Ukraine, I think. He is apparently working on an AI tool to, and intelligence is a little bit thin on the ground as far as this is concerned. But I believe he's trying to build a tool to identify people of color who are based in the US and get immigration and customs enforcement to go and deport them. So we're hunting memes, they're hunting people, and that's probably the best description of Nazis versus everyone else that I can come up with. Any other questions? Thank you.